Analytics. My name is Derek. I'm with Corporate Analytics, Chief Operating Officer. We are part of the Sidara family. Thanks for being here. I appreciate your time. Really, what I want to do is talk through the umbrella of building energy management information systems and then the categories that fall under that. I know some of you here have already expressed your interest in building analytics. So my intent today is to give you a preview, a high-level overview of what it can do for you, go into some specific examples, and then wrap it up with a Q&A. All right, so let's get right into it. If you look at this slide, this is from Better Climate Challenge, USDOE, a very recent publication coming from February 2023. The whole idea here is prioritizing GHG measures within buildings. So you can see priority number one is avoiding or using less energy, kind of common sense. The best energy you save is the best energy you don't use. Then there is two, which is pivoting to low carbon solutions, so electrification, GWP, refrigerants, all of those low processes in terms of carbon emissions fall under that category. Then there is sequestration, carbon capture, that's number three. But everything that I'm going to talk about today falls under this umbrella, which is priority number one. If you have a building, if you have a built environment, then really you can achieve a lot of savings by employing technology that will help with reducing emissions and saving energy. And that's what we'll talk about today. So if you look at this diagram, within the umbrella of energy management information system, and so I'm going to use the terms building analytics and EMIS, they're kind of synonymous. Under that umbrella, there are four different categories of technology. So one is pattern analytics, then there is energy information system, fault detection and diagnostics, and then automated system optimization. Here's the thing, for any of these technologies to work, you've got to start from point A, which is getting data out of the different building systems. We talked about this in a previous panel earlier today. The whole idea being the data sources come from different places. So you have utility bills, maybe that's automated in that you can pull that data from a utility through API integration. Maybe that's manual in some cases. There is interval meter data available, weather stations, building automation systems, so all of your heating, ventilation, air conditioning systems, all of that come under BAS. You can have IoT devices. There is investment happening in terms of if you have a building and you don't have enough sensors, you can invest in technology to monitor indoor air quality, monitor other different sensor information that you want to gather and then bring on to your building energy management information system. Distributed energy resources, the list doesn't really end there. There is tons of sources of energy you can tap data from. And all of that data goes through a data warehouse, sits in a platform, ideally in a cloud environment where you can deploy advanced analytics on it. So this is where we talk about machine learning, artificial intelligence, all of those technologies that are available today to really enhance the way buildings consume energy in terms of bringing the intensity of carbon and energy down so that the performance gap we see in buildings, the idea is it shouldn't exist at all, right? When you design a building, when you construct a building, you say, well, the energy intensity and the carbon intensity should be this number. We work on several projects where even a year later, you're not talking about 10 or 15 years later, even a year later, that intensity number sometimes is much higher than what was initially predicted or modeled. And that's just the way buildings work, because there are lots of changes that happen in a building. When occupants come in, there are scenarios that perhaps weren't considered when the modeling took place, and then you have a performance gap. And the owner of the building may ask the question, wow, this is not what I expected to see. How can I bring my emissions down? How can I bring my consumption down? And so once you have all of the data, and data is the key. Without data, all of what I'm talking about does not happen. And so you need a technology that's able to collect data from multiple sources, bring it all under one umbrella, and then ideally, these technologies can be part of one platform, right? You don't need to go look at multiple user interfaces to derive benefits from pattern analytics and fault detection diagnostics as an example. All of that can sit under one umbrella, one platform, a unified user interface, and you can get the benefits out of it. So let's look at a few value propositions. So why would you need this? I talked about energy overall, but number one, unlocking power of data from multiple sources. So this is key. We talked about it. Whatever source of information you have or data you have, the technology must be able to tap into that either through APIs, through a device, or in one way or the other, get that data out from your individual systems to the cloud platform. Number two is enhancing commissioning and building performance. Forget about a building that's fully operational. Even when the building is in the commissioning stage, so if you have a building that's just under construction, the construction is done pretty much, occupants haven't necessarily moved into the building, there is a commissioning exercise that happens to ensure that all of your equipment is working correctly. You can deploy analytics right from that stage. So it does not have to be in a fully occupied building 2 years, 3 years down the road. And that's an important distinction, because sometimes there's a thought process that, well, my building is only 2 years old. Why would I need analytics? Well, even in the commissioning phase, you can deploy analytics, because for a building that's 200,000, 300,000 square feet, you have systems that are closer to the human beings, right? We call it the terminal units. There are tons of them in any building. And with commissioning, which is data-driven, you can achieve about 70 to 80% reduction in labor when it comes to making sure that equipment is working properly, things that are not right or issues are surfaced very quickly for someone to action. We talked about energy efficiency and reporting, and the reporting element is important because at the end of the day, you need to save energy, but it's equally important to make sure that you're reporting on the achievements or the successes you're having within the building. Improving occupant comfort and safety, that's not, energy and occupant comfort, it's not either or, it has to go together. And a good technology will allow you to do that, will allow you to reduce your consumption while improving your occupant comfort and safety. Maintenance service, reducing costs. This is important in that a lot of organizations that we work with, they have very high deferred maintenance. Sometimes there are hospitals that we work with where deferred maintenance, and university campuses where deferred maintenance, and this number is high, is $1 billion. That's huge because there's many systems across different campuses that haven't been touched or worked on because there is a lack of money, and you need to know exactly where that money needs to go. If it's a huge university campus or campuses under an umbrella where you have 4 or 5 different sites, that's the kind of money you're talking about in terms of what's already there that should be fixed, but without a tool that allows you to maintain and help with it, sometimes it doesn't happen all that well. Now, when you work on maintenance, improving it, reducing the costs associated with equipment replacements, really what you're doing also is prolonging the lifetime of your equipment. So you can invest in a very sophisticated chiller, and it's supposed to last 15, 20 years. But if your chiller is cycling way too often, and if it's not working correctly, it degrades the lifetime of the equipment. In fact, the chiller may only be operational for about 10 years. So there is value in making sure that your equipment runs well, and that during the lifetime of the equipment, any issues are detected quickly so that you get the value that you invested into the equipment. Now, how does it all work? If you look at this diagram, this is the different data sources that I talked about, a building automation system perhaps, different types of systems, escalators, elevators, irrigation system, whatever you have it in terms of where the data comes from. Primarily, heating, ventilation, and air conditioning system is important. That's where we primarily collect data from, but other data sources as well. And then all of that data is collected by a device which can either sit on site or off site. It does not always need to be on site. Now, again, there is technology available where you don't need a device, a hardware to pull data out. You can use cloud APIs. So if all of that data is available in a cloud, why use a hardware on site to pull that out, right? You can use API integration, cloud to cloud, and all of that information through a secure firewall comes into the analytics platform. comes into the cloud platform. Now, once that happens, really, that's where all of the magic happens. That's where AI, ML-enabled algorithms are automatically applied on the data set to convert all of the data into useful information. Now, once the information is there, of course, users can log into a UI and access that information through an online portal. It could be automated reports, so sometimes there is no interest necessarily to log into the platform and look at it. You just need to, you're busy as a building owner or a facility manager. There's tons happening. You don't have time always to sit in front of a machine and look through all of the problems. So you should be able to, with the use of technology, be able to alert you whenever something of interest happens that you're interested in, right? There may be 50 different issues in the building. What are you interested in? The system should be able to tap into that and alert you whenever that happens. Now, just to give you a scale of data, because whenever we talk about data, it's amazing how the scale matters. So what you have here in this example is a sample air handling unit, okay? So you have a graphical view of the air handling unit. You have the supply duct, the return duct, the fans, the coils, all of that inside it. What I really want to share with you is the scale of data. So look at this. There is one air handling unit. If you use this one as an example, that could have about 30 data points within the air handling unit. So that's your coil, your temperature, your pressure, your set point, all of that stuff. That's about 30. Now, if you're sampling every 5 minutes or 15 minutes, you have as many as 3 million data samples in a year. Now, that's only one air handling unit. If you have 1,000 similar assets in your portfolio, you could actually be dealing with 3 billion data samples. There is no way a human being can comb through all of that data and identify issues that are happening in the building. And this is precisely where technology helps. This is precisely where the energy management information system that I'm talking about with the 4 different categories can pitch in and help, because you really do need a sophisticated platform. You really do need a dedicated analytics platform that will do the job for you. You can sleep well knowing that your buildings are being continually monitored. And anytime you have an issue, anytime there are severe issues happening, the tool will pick it up and it'll report it. Now, I talked about 4 different categories under EMIS. Number 1 is pattern analytics. So really, what is it? Analytics uses tagging, and that's an important item we need to tackle or talk about. It uses tagging and contextualization to monitor different trends. So we just talked about 3 billion samples for 3,000 assets. So it monitors automatically all of the trends associated with different systems, and it detects anomalies very quickly. So how does it happen? Well, here's a very quick overview. I'm not going to go into the details today, but there is a discovery process whereby you say, well, show me everything that the building has. If wherever you have the data, show me everything, discover everything. And then there is an automated mapping and contextualization process. So that's where if you have 3,000 points in a system, how do you group it into different buckets? How do you bring all of the air handling unit supply fan data into one bucket, the return fan data into another bucket, your coils into another bucket? All of that needs to happen in this stage with mapping, and then contextualization, which is even more important. The fact that you group something into different buckets is not important. It's not the end all. You then need to make sure that there is meaningful data wrapped around it. How will other systems look at the set of data you have in a container and interact with it? And this is where technology helps. And then once you have done all of that, you move into the next stage, which is modeling, right? Now you have data. That data is not incomplete. We have done some cleansing on the data, some grouping on the data. It's ready for you to do something with it so that we get meaningful information out of it. And modeling, this could be automated rules, AI, ML, all of those technologies go into play so that we get the benefits we need from it. I didn't want to leave you guys with just the talk. So what I have here for you is an example. You're looking at Coppertree's cloud platform, and we have an example here. These are all real sites, real buildings. This is about 10 plus fans in a building, okay? Multiple fans from different air handling units. In this case, you're looking at a makeup air unit. What you're finding here, and this is what pattern analytics can do for you, you'll see the pattern typically, which is system start, system off, right? Turns on in the morning, shuts off in the evening or the night. Now, there are two fans right here where during a period of time from March 2020 onwards up until about June 2020, the fans did not stop. You don't need a sophisticated AI ML platform to be able to catch that. That's basic pattern analytics. Because you can look at what happened in the past. Well, in the past, the fan turned on and the fan turned off. Now, contextualization, tagging, and the other technologies come in play, and you can say, well, my supply fan here has to kind of behave the same way as the other supply fans in the building. So this is where you get that kind of result where everything is compared with each other. The use cases are explicitly stated, and things of interest are brought to the surface. What happens in a case like this? In this example, we pulled data sometime in June 2020. We did have the history, and right off the bat, you're able to detect something that's wrong, and then what we are after is this: real changes happening in the building using information that's coming out from the system, where a fan that was running 24/7 now shuts off during the night. It has to start from small changes. Before it gets to the building level and it has an impact in your utility bills, it starts with a fan, it starts with a pump, it starts with the smaller systems before it gets to that stage. Now, let's look at the second category under Energy Management Information Systems, which is Fault Detection and Diagnostics, FDD. What does FDD do? Well, the main thing here is that, of course, it detects faults and issues in the building. It prioritizes them. That's all good. But the key thing I want you to take away is that it's typically a one-way interface with the building automation system or the data source, in that it receives the data, it analyzes the data, and it pumps out information or results for the end user. So it's a one-way interface. So that's how we're going to differentiate FDD from something that I'm going to talk about in the next few slides, in that, yeah, you can detect issues in the building, prioritize them, all of the magic, but it's a one-way interface at that point. Here's an example. Now, if you look here, we moved from looking at similar trends in pattern analytics straight into some advanced algorithms. What you're looking at is a chill water loop delta T analysis. So for those of you who are familiar with chillers or boilers, you know that these equipment have temperature, water or whatever other process variable you're tracking, temperature going out, temperature coming back in. If you have really low demand, then the temperature differential between the two loops will be very low, because you pumped water out at a particular temperature. There was no heat gain or heat loss, right? In this case, it did not give cooling anywhere else, and that's what we are tracking here. So in terms of reporting, analyzing just one chill water loop, what you have here is delta T being calculated. We have different bins, 0 to 2 degrees Celsius, 2 to 4, 4 to 6, and so on. We also have a bin which tracks hours when the chiller or the chill water system was turned off completely. And this is the interesting part. You can see on a daily basis that's 24 hours. Makes sense. So you have I think this is a Sunday, and the last day there is a Saturday. So on weekends, you have the plant completely turned off. And then this is during the shoulder season. I actually captured this image just before I traveled here, end of November. What you're seeing in this real world building is during the, this building is located in Canada, and you can see during the winter season, there is really low demand. The temperature differential between the two sensors is really low. So you don't really have much happening in terms of cooling being provided. More importantly, cooling being needed. And because cooling is not needed, why would you run your chill water system, right? That's the whole idea, in that you can now use this information, present it to the guys, the girls running the building, and say, hey, you have an opportunity here to now configure the system, change the sequence of the system so that when your building does not have enough demand, then you can actually turn down the system. So let's look at a couple other things. Now, when you have all these different insights being surfaced, insights are anything that's important to you, right? Any information that's captured, that's a problem, issues, they surface in the platform, and you're looking at a page where a lot of these issues show up. And what's important is that it's not enough for you to see a list of issues. What is important is that these issues are prioritized. For an energy manager, the priority is to bring down their energy cost. For a facilities manager, the priority is to make sure that maintenance moves from being reactive to proactive, and that all important issues are addressed right off the bat. So different users have different requirements, and that's important. Because again, with a platform that's really helping users, you have different user groups. And for each user group, the requirement is different, and the platform must be able to cater to those unique and different requirements. In this case, you're seeing a small building. I think this is about 100,000 square feet, so very small building. You can see a bunch of insights or issues that have surfaced, potential cost savings, which is amount of money you can save over the year if you were to tackle and fix the issues right off the bat, right? So that's the use case. And then I won't go into the details, but in real world, when buildings are operated, you have work order management systems, other platforms that the building operators use to tackle these issues. So it's also important, again, for all of the information that's in your platform to be sent, if needed, to other platforms where it can interact with the users who are actually consuming all of this information. It's kind of pointless, isn't it, when you've invested into a technology to identify all of the issues, and if the operators are used to looking somewhere else, the technology must be able to pump all of the useful information into that third system if there is a need to. If it's a work order management system, so be it. So that's one of the ways you can visualize all of the insights or the good results coming out from the platform. And it does not stop there, right? Now, you know that this particular issue is supposed to save you $6,000 a year, as an example. You don't stop there. You go and fix the issue because that's prioritized for you. Once the issue is fixed, what's equally important is that you measure and verify the savings that are coming out from that resolution. So in this case, here is a sample of sample report for a building within our platform where the actual gas energy is being compared with baseline gas energy. The gray bar and the red bar, if you can look at it, for every month from 2022 onwards until 2023 November, the gray is the baseline. And so you can see, during these months, as an example, the gray, which is from previous year, that is a very high number compared to the actual usage. So you can continually monitor how you're doing, how are you performing, because the last thing you want to do is make changes or implement ECMs, energy conservation measures, and then wait until the end of the year to find out if it worked well. You need to be able to track these things on the go all the time. So if you have a requirement where you need to look at it weekly, monthly, quarterly, feel free to do so, right? Because the tool will automatically do all of that. If you're interested in having this report be sent to you as a PDF, as an email, the tool will do that as well. Now, so that's FTD. Before I move into the third category, I wanted to talk about sustainable retrofits. The whole idea being, when you're implementing all of these measures, there is energy being saved and therefore operational costs being reduced. This stat is important. Retrofitting 20% of the existing building stock by 2030 is an ambitious goal, but it is necessary toward the net zero emissions by 2050 scenario, right? All to say, in about 7 years, we are in 2023 now, in about 7 years, or 2024 pretty much, in about 6 years, you need to retrofit 20% of the existing building stock, and that's a lot. That's a lot of investment. That's a lot of technology use cases out there that we can tap into. And that's why the whole idea of savings and the amount of money you're saving with retrofit measures, using that and putting that into more measures so that more savings are achieved. And then using that money further, putting that into even more energy conservation measures. It could be capital investments. Whatever that is important in that we have a target to hit. And so to get to the 2050 target, we need to get to the 2030 target, which is sustainable retrofits of at least 20% of the existing building stock. Now, let's move on to the third out of the four categories under EMIS. This is automated system optimization. If you remember when I talked about FTD, I said that the distincting factor is that it's a one-way interface. With automated system optimization, the system becomes even more intelligent if you subscribe to use this technology, which is it can write back to your building automation system as well. The key word here being, you'll be able to dynamically modify building automation system control settings to optimize energy consumption while maintaining comfort. So the dynamic modification comes through the automated changes that the tool is able to do. So now you're not just reading data, now you're not just transforming it to information. Now using the information, I like to sometimes say it's really wisdom, right? It's not even information at that point, it's wisdom in that it actually tracks those changes, implements those changes, and you'll be able to get the full result out of it, all the benefits out of it. I want to show you a couple of examples, but before I do that, this is traditional fault detection diagnostics. So if you just had a traditional use case where you have the system being monitored, data collected, this is how many, these are the points at which human beings are involved. So when a fault is detected, someone has to evaluate it in the traditional workflow. There's a human being there looking at an insight or a result in the platform, ensuring that, yeah, is it right? Can I validate it? Yes or no? Once that's done, someone's got to go and execute it, right? There's another human being, at least, maybe more, involved in that process. Once they execute it, you've got to track it. So there's even more people involved. In the building sector these days, one of the key things that challenges is that you don't have enough skilled labor. You don't have enough people trained already to take care of our buildings. And buildings overall, 40% of emissions come from buildings. So for us to get to the targets that we have set for ourselves, we can't rely on a lot of time within the operator class, within buildings, to go and fix issues, to go and monitor issues, to go and track issues. No, they can't do all of that. This is where technology comes in. I'm going to bypass the two flows in the middle here, go straight into the last one. In a fully automated system where ASO is completely deployed, what you get is the system is operational. You have the FTD system running. It auto-calculates everything that needs to be calculated, and then it writes back to the building automation system based on the information it has collected. Right? This action execution is key in that no human being is involved in that process. Now, you can, at the end of the day, still track it, because you need to validate, is it working the way I want it to work? Are you building that trust? You can still track it at the very end. But you have now saved a whole lot of money and resources, and the resource component is really key by going the automated system optimization route. Some examples, again. If you look here, the first slide that I have, it's a static pressure reset example. I'm getting a little technical within the air handling unit system here. You're looking at two main trends of interest. One is the red trend log, and then there is the blue trend log. The red trend log is the discharge pressure set point, and then the blue trend log is the discharge air pressure itself, right? So what you're looking at is a set point that is consistently reading one value. It never resets. And why is resetting important? Well, within the building, there are times when there are more people, times when there are fewer people. And based on the changes in the building, you should actually be controlling and running your equipment differently. In this case, what we did with ASO is you had a situation like this. Well, ASO can actually look at what's happening in the zones where real human beings are. And when there isn't enough demand, you can begin to reset your pressure. And when you begin to reset your pressure set point, right, that's the red trend log, you can see the pressure actually follows the set point. All to say, when that happens, your fan is running at a reduced speed. When your fan is running at a reduced speed, there's at least three things happening. One, you're saving on electricity. Two, you're saving on thermal energy, because the air that's passing through the valves, it's not picking up as much heating or cooling, whatever that be. And thirdly, when your fan is running at a lower speed and running fewer hours, there is savings on the equipment itself. It'll last longer for you. Now, I do have a comment here. These are one or two examples that I'm showing, but the scalability piece is important in that you should have a system that can be applied. The ECMs that you're looking at must be applied and should be applied to multiple systems at the same of the same type automatically on scale, right? That's really when you can get thousands of dollars worth of savings, because you have something that's proven. You can test it, implement it on scale, on many systems all at once. And then the last one. The last one is energy information system. And what it really does is it allows you to visualize your energy consumption, track it, monitor it, do advanced analysis on it, so that if you have a portfolio of buildings, you can detect what are the buildings where you are consuming more energy, you're spending more on gas, electricity, et cetera, so you can make decisions that are informed in that, hey, out of the 15 buildings I have, my money should go to this building because this is consuming way more than the other, right? That's the whole use case. Again, an example. You're looking at a school district in Vancouver, actually, and what you have here is an analysis done with electricity. So that's electricity consumption analysis. You're looking at a baseline and then the actual consumption. The baseline is in the green here. That's about 319 megawatt hours. You have an actual consumption that's shown as less than your baseline. And in this case, that's about $3,000 of savings. This was soon after COVID that this analysis was done. Here is the catch. And the reason I brought this example with me is to show you how COVID has affected things. During COVID, one of the things, as we know, that has happened is the occupancy in the buildings have changed. Previously, when COVID wasn't the term that any of us knew, just weather normalization was enough. Because comparing 1 year's data to the other, the only thing that changed was weather. Not anymore. Now you have changes in occupancy, and in this case, we did an analysis where automated through the tool, where instead of, because we did not have occupancy meters in the building, occupancy counters in the building, we did use carbon dioxide sensors. And with carbon dioxide sensors, you get an impression of how many people are actually in the space. And what happened is, in the previous slide, if you remember, it had told us that was $3,000 savings, but in all reality, with the decrease in people, the system should have consumed less energy, but the system was consuming even more, right? So these use cases are automated. You may have sub-meters in the building, utility-grade meters in the building, many, many meters. All of these systems are continually being analyzed, and results are being brought forth. I'm going to wrap up my presentation. Now, if you have these technologies already, or if you're looking for an EMIS technology, what are the kind of savings you should be expecting? This document, or this capture that I have, comes from LBNL, Lawrence Berkeley National Laboratories. We work very closely with them. They're funded by the US Department of Energy, and this is from October 2020. The Energy Information System, the one that I just talked to you about, you should be seeing about 3% savings with the use of that technology. And with an FDD system, you should be expecting about 9% savings. And even though the investment or payback here is shown as 2 years as an example average, our experience working on buildings around the world is that it could be in a matter of months, not years. You don't have to wait for a year or 2 years, because the investment that goes in and the amount of return you can get out from simple changes. These are not capital changes that your building requires. These are simpler changes. There's a lot of opportunity in terms of how much money you can save. The last thought before I wrap up. Technology is very important. And at the end of the day, it'll work for you if you deploy it correctly. But equally important is resources and culture. So if you're considering an EMIS platform for your buildings or your portfolio, you need to make sure that I define culture as the collective thinking of the people that's using the technology. They should all be aligned in that, why are we using this technology? And how can the operational workflows be tweaked or changed in order to make sure that maximum benefits from the technology are achieved? How can the resources be aligned, their daily workflows be tweaked to make sure that ultimately what the technology promised is what you get for your buildings? Thanks for your time. Thanks for listening. If you have any questions, I can take them now. Yeah, go for it.
Thank you for the presentation. It's impressive how the data can work to reduce the energy and reduce the carbon. My question is, will there be a benchmark with building types of, and if I am a client, I am having an office building, in that region, will the platform provide a benchmark of similar office building in the same region to check if I'm going in the right direction?
Thanks for the question. It's an important one. Absolutely. Benchmarking is key because you can have, let's pick on a university campus as an example. You may have buildings with a lot of lab spaces. They may be 200,000 square feet in terms of size, but the actual consumption within the building will be way higher than a 400,000 or 500,000 square feet building, which is an admin building. And so it's really important to make sure that when you're comparing buildings, weather normalization, all of the other normalization elements that we talked about, they still apply, but you've got to group the correct buildings together. Otherwise, you're not comparing apples to apples. So it's important. And then the jurisdiction or the geographical layout of the campus is important. Sometimes you just look at the amount of money you're paying, but the amount of money you're paying, if you have portfolios spread across the country, is not a good way to compare your buildings. Because one utility may be charging you a higher amount than the other utility. That doesn't mean that the building with the higher cost is actually consuming more. It depends on the rate, right? So there are and the types of rates. There's demand charges, there is consumption charges. So you have to look at a few different parameters to make sure that you are indeed comparing apples to apples and identifying the buildings that need attention. You had another question?
First, thank you for Cooper Tree to come all the way and to give us this magnificent presentation. My question, as you know, Abu Dhabi and Al-Khubar is the highest wet bulb temperature in the earth. Now, after you start your installation in United Arab Emirates, did you expect to see more data or more data analysis or more data R&D with your company? Be totally different than what you used to in Canadian environment or Singapore or whatever is the two main base your company is working with. Did you expect to see abnormal data or to do more analysis, more R&D in the company for this? Second question is about district cooling. You know, many building here is connected to district cooling and suffering from low delta T syndrome. So did you have, are you going to do R&D to formulate with UAE or the region here, even all of it now with district cooling connection, that is the building will start to have index for it, benchmarking and all of this? Thank you a lot. Thanks
for the question. Yeah, first, research and development, it's an important piece to the puzzle in that the tool should continue to evolve, right? It's not a static tool because there is more technology being developed, and the technology that's being developed needs to be included into the tool so that you're future-proofed. You don't want to invest in a technology that doesn't change and upgrade. And that's the beauty of cloud platforms, because when the technology changes, your cloud platform can be upgraded to the latest and greatest technology. So that's one on the R&D side, and we fully believe in that. With your specific question, which relates to Abu Dhabi, Dubai, this region and the countries here, yes, the tool that we've developed at Copper Tree, it's able to analyze data from any building, any region, and the technology goes into play in that as it collects data, doesn't matter from which region, you analyze it for the conditions outside, because the weather data is pulled in from the region, the humidity data, wet bulb, dry bulb, all of that is pulled in from the region. We have a triangulation method whereby we look at the closest weather stations, 3 of them, to pull in exact data that's most relevant to your building, and then the analysis kicks on. And so you're not really, basing all of your analysis on what a building in Canada or the US or in Europe could look like. You're actually basing all of your analysis on data exactly from the region and very specifically your building and the portfolio that you carry, right? So did that answer your question? You're welcome.
Thanks for your presentation. Regarding the FDD, the fault detection and diagnostics, the rules which are written by yourself, it do the root cause analysis from any backend. Example, as sir mentioned, in UAE we face a lot of low delta T syndrome. So low delta T syndrome can be based on the different root causes, not maybe a low chilled water flow or other things. So how the fault detection and diagnostics works from that end. And then again, second question is, you showed that the savings is coming around 9% from the FDD. How you will be proving that 9% of savings from by M&V, which option you will prefer, or it is a theoretical number you are just presenting over there? Because example, you are doing a chilled water reset, okay, for the each AHUs you are doing. Example, in Dubai, you can see around all the buildings will have 100, you will have 100 AHUs and FHUs. How you will measure the set point adjustments? Because you cannot install the BTU meters for each and every unit, and the cost of metering will go very high. So how the 9% can be done from that?
These are excellent questions. On the measurement and verification side, in all reality, our approach is when you have sensors that you already have, use it. And then sometimes you've got to make assumptions. And the assumptions need to be reasonable. Ultimately, at an equipment level, you can make all of the assumptions you want. You can calculate savings. But ultimately, your utility bill data should show it. And that's the best way to validate that your calculations at an equipment level is correct. Because when you have 15 air handling units in the building and 12 of them were worked on, you can have as many M&V approaches for your individual air handling units. Your utility bill should be lower, right? And so that's the key. So assume when you can, based on the best information you have, because even outside the EMIS platform, if you were doing a site audit, you'd have to do that. There's information you just can't have, or data sets that you just do not have access to, so assumptions need to happen. The cool thing is, at any given time with an analytics platform, let's say you made an assumption that was inaccurate. It could happen in the real world. It's, you thought that this particular system is supposed to be feeding, to 50 VAVs, but it's only feeding to 30 VAVs. It's a change, right? It's not something that you anticipated in the beginning. What you can do is, with an analytics platform, make the change in the rule 16 days, 16 months after the fact. With the click of a button, it'll go back and rewrite all of the calculations, right? So that really helps you in that you're not now basing your results moving forward on the incorrect assumption you had made. You clicked a button and changed, well, this assumption was wrong. I'm going to replace that with a new one. And all of your all of your history is now taken care of because it reset all of that. And your future calculations will use the new assumptions that you've made. And on the district energy side, completely understand. Ultimately, when you have a district energy platform, district energy system, you don't have a heater and a chiller, or a boiler and a chiller. You do have heat exchangers. But the science behind it in terms of differential pressure resets or the fan speed resets, they all run the same still. And so you can take evidence from what you've done elsewhere and use those same principles for a district energy system as well. On top of that, when it comes to district energy systems, one of the things we look for is within your heat exchangers, because your delta T regulation requirements for a heat exchanger is much lower compared to a full boiler or a full chiller, because you would expect way more delta T. So changes like that based on the equipment is already factored into the system. So you're not running with your 0 to 5 degree example that you use for a chiller or a boiler when you're working with a district energy system. So those changes are automated. The system understands that this is a heat exchanger, not a chiller or a boiler, even though it has a supply duct, supply loop, and a return loop. It takes that information and caters to it differently. Any other questions?
Thank you, Derek, for this great presentation. You've mentioned a 2-year payback period, and you've also mentioned that it could be just a few months, that the payback period could be reduced to a few months. So what are the key drivers to having such a very good and low payback period, 1? And 2, how do you see this can be tailored to the Middle East? Like, how do you see, will the payback period be affected in another way if we are to use that same tool for projects in the Middle East? And then one last point. Do you see a difference between having it in an airport facility versus having it in an office facility, for example, or residential facility?
Remind me if I lost a question in the mix. But I'll tackle one of the questions first, which is, how would you get to savings quicker, faster, and get the payback number lower? It really is based on how many of the changes being recommended by the platform is actioned. And if you have ASO, and this is where ASO becomes very important because with automated system optimization, you can automatically write back. And so if there are sequence changes that are needed, or a pump was put in manual by an operator and they forgot about it and the pump is running at a high speed all throughout, with ASO, without having any human being involved in the mix, you can rewrite it, right? And so you can get to savings quicker. Otherwise, you are sending a work order to someone to go to the site and change it. Takes longer. If they have other priorities, they may not get to it. And so ASO, I think, is key in terms of getting to savings quicker. And if you don't have ASO as part of your technology framework, you can still get to savings by having a philosophy in place and a culture in place within the organization that, hey, when you get insights or insights are surfaced in the tool, act on them quick. But you can't expect your team to act on them if you haven't changed their workflow. So for leaders in our industry, it's key to make sure that not only do we invest in the technology, we also invest in changes in workflows, changes in the way people operate on a day-to-day basis. What was the other question again? Did airports, different types of buildings? Yeah. So in terms of what can you expect from a airport, healthcare facility, offices, etc., you get savings from every building, of course. But what we do find is there is a whole lot of savings that's achievable from healthcare, way more because the systems are much more complex. And when systems are complex, more mistakes happen in the way the equipment and the building is run. And so it's not a human's problem. Mistakes happen because people are busy, they put things in manual or something is just tweaked incorrectly. But ultimately, the system can be automated enough to go and fix those issues. So yes, it helps if you have a building that's way more complex than the other one. And you could possibly get way more savings from your complex buildings because chances are it's not maintained and operated the right way. Yeah. Any other questions, comments? All right, thank you everyone for your time. Much appreciated.